Okay, so it seems that we are live. Good to see you, or not to see you all. We will start. I hope that you see the presentation, and good morning, or good afternoon, in fact. I wanted to talk a bit about my small educational project, which I did some time ago. And during that project, I wanted to teach computer to play computer games so I don't have to. And the subtitle of this presentation is and why such a bold statement? By no means I want to limit you just to watching this presentation if you are interested in machine learning. But during my small undertaking, I encountered many problems which you most likely will also encounter when dealing with the regular data science machine learning project. What was funny with that project was that the games are funny, games are fun, and moving something physical have a lot of, I would say, magic in it, because it can you can clearly see whether your model, your machine learning solution works or not. You see if the ship, as you will see in a minute, or not. But let's go into details. As you know, my name is Adam Dudczak. On a daily basis, I work at Allegro. Allegro is the biggest e-commerce site in Poland. I am responsible for the development of search engine, and as such, I'm also involved in projects created using Java since quite a while, and from time to time I'm also writing something with Python. I'm heavily involved in Polish and Poznan Java user group, and also in my free time I'm helping to organize a conference called GeekOn. So that's more or less all about me, and let's start to talk about the project itself. So where to start? I wanted to teach computer to play games, so I had to do modeling in Python. So I limit my search just to games implemented in Python. And this brought me to Pygame, which is a well-known and robust, well-documented, robust library, which helps to deal with all the scaffolding related to implementing a simple arcade game. So all the things related to loading assets, to managing them, to detecting collisions, to physics, to music, this is all handled by Pygame, and it allows you to create an arcade game in 100 something lines of code. So neat, and there are a lot of games developed using Pygame available. I took the game called Bradfield in series of articles in which Chris is doing a marvelous thing. He shows kids how to use Pygame to develop their own game. And I encourage you to take a look at this series of articles. I took one of the steps and used this for my experiment. This is a technical conference, so let's take a look at some source code. Here you see those boring scaffolding lines which you need to do, which Pygame helps to deal with. So loading assets, initializing game window, initializing game objects. This is all handled by Pygame, and here you see the main game loop. Nothing fancy, nothing complicated. the loop goes infinitely till the object is alive. We have the section from the keys pressed by player. Then we update the objects related to the game. We're detecting collisions, adding new objects, killing the one hit by a laser bullet. And when everything is ready, we draw the frame and go this once again. So once again, nothing really hard. But the question is, since this is the machine learning presentation, the question is what data is relevant for this particular problem? What data do we need to teach computer to play the game for us? So let's take a look what we have at our hand. Here is the game window. The window was a fixed size. So we have the following coordinate system in which we have the position of the ship. To simplify things, and it has an infinite number of bullets. So we also have a position of the asteroids, of mobs, and we can calculate the distance from those asteroids. And last but not least, we have the coordinates of our bullets, and we can also use this data. But I decided to start with something simple. I decided to use things like the position of the player and also the position of the mobs. So this is a pretty limited view of the world, but let's start with something. So this is the representation of the game state. In fact, this ends up like a 20-something digits long vector of numbers. And or which action to take. And in fact, we have 6 possible actions. We can move left, we can move right, we can fire, we can also do nothing, which is also an option, and we can move and fire, which in most cases will be the most effective move. So we have a vector of numbers, as we usually frame problems in machine learning space, and we have 6 classes. So we need to classify those vectors, those observations, into one of 6 classes. So this is a classical classification problem, and as a classical problem, it has also classical solutions, and we will get to that point in a minute. But before that, we need to get training data. Since we have the idea what will be the representation of the game state, we need to get training data. How to do that? I decided that I will without state representation with every frame, and while I play the game. So in fact, I am generating training data by playing the game. We couldn't omit that. Some portion of playing for the computer, some portion of playing on our own is necessary here. So so here you see how I plugged this into the in game objects. Here you see simple Python classes which are responsible for handling the state of player and for the asteroid. I'm dumping those data with every frame and output them, as you see here, to the standard output. Apart from dumping functions, we need to also plug this into the main game loop. So training data. You can save that to some fancy database, but for this particular project, standard output sounds like a pretty decent database. So I made a copy of Shmoop, which generates those dumps with every frame, and save this into the training log, which looks more or less like this. I've also added one thing at the end, as you see here. So I am also, the last arrow here, I am also saving the amount of killed asteroids to rate a particular game to get the score. Here you see the vector of numbers. The last one is the action. which was assigned for the given state of the game. And since we have the game state and we have training data, we can the link in Jupyter Notebook using libraries like Pandas and scikit-learn, which are also well-known, documented, well-documented libraries, which helps a lot here. So thanks, we are loading data from a CSV file, which I created on top of the training log. Here you see that we have 760 observations. This is certainly not a big data, but it's something to start with. And I wanted to test if this amount of data, more or less 3-4 minutes of playing, would be enough. So what do we have here? Here we are using the scikit-learn magic. We, in first place, we are using the train test split. So the data created during my manual play are split into. So in fact, 4 arrays. In the first one, X train, capital X train and Y train, these are 2 sets which contains X contains all the entire game state, so the entire vector of numbers, and the Y train contains the class which was assigned. We have train and test set. One will be used during the training and one will be used for evaluation, as it is not to see how our classifier deals with observations not seen during the training. Then we have a logistic regression, which has several parameters, but we will stay with this what is here. And classifier.fit is in fact training itself. Nothing complicated, you would say. Yeah, as long as it works. We will see that in a minute. Scikit-learn contains a lot of methods which allows you to evaluate your classifier or your regressor in a simple way, and accuracy is the simplest metric used to measure the quality of classification. So O.78, so 78% of accuracy, 78% observations were classified correctly by our classifier. This is the score on the training set, and on the test set, the score is a bit lower. Is it enough? Is it good? Is it bad? We'll see. Then we save the model into the file, which we need to plug into our game. So I made another copy of the source code of Shmoop, and in a way that I'm loading the model. I have a method which gets the game state, and on top of that game state, it invokes the prediction. As a result, we get the action which needs to be conducted, and this action is in fact passed in the game loop in place when we will usually try to read the keys pressed by a user. So also nothing fancy here. And here you see the first results. It shoots a lot. It looks marvelous. Nevertheless, this particular one looks it looks dangerously, but this one, which you see on the right, is in fact a random agent. I thought that the project is nice and I have a lot of fun, but it would be nice to have the generator. It returns one of the 6 possible numbers and use this as my smart agent. On the left side, you see how our logistic regression performs. So this is not yet a prototype of the Evil Skynet. If one can play that game poorly, logistic regression plays it very poorly. So not yet. What we've done wrong? Maybe the model was too weak. Let's try something which is more state-of-the-art, more complex, random forest classifier. This is a different concept. This is based around, in fact, two concepts, a decision tree and a model ensemble. So the idea is to have several smaller models trained on a portion of data and a portion of features, and use the large amount of such a small, simple classifiers. As you see here, number of estimators is 1,000. So we have 1,000 of trees in this forest, and the final result, the final classification, is created on top of as a result of voting. So this is in fact one of the state-of-the-art solutions, and decision tree is a very nice tool. It can process all kinds of data, and it gives distinct results very quickly. So it is also a good baseline. A random forest is an example of bugging strategy when you ensemble several decision trees. There's also another approach which is called boosting, and it's a bit different way to of trees. So imagine a situation in which we have this first simple tree, which is able to classify some portion of observations correctly and other not so well. So we are just taking those observations which were classified in the wrong way, and we train another tree on top of that data to minimize the error. And the whole thing is repeated several times till reaching the certain level of error. So let's go. Here you see the training accuracy. It is quite high. Of properly classified observations, and it looks very promising. So let's see how this model behaves. Starts pretty well, but then goes into the corner and waits for death, like our previous attempt with logistic regression. So something else here is wrong, and we need to investigate what. But before that, I want to tell you a bit more about some two terms which are important and overfitting. Underfitting is a situation in which we are using a model which is too simple to understand the patterns which you want to recognize. So let's go back to logistic regression. This is the simplest possible classifier. And it seems that our game representation, the size of the solution space is too big, or the amount of data is too large, too small, I'm sorry. And what? And we need to come up with something different. So in practice, when you see that, it looks like having a small accuracy, poor results on training set. I'm sorry, because we have some technical problems. Moderator is asking me to do. I will turn off the camera just to check if this would help, because as I hear the slides are lagging. So another approach is the overfitting. Another term is the overfitting. And overfitting is a situation in which we can compare to student who learned by heart the question from the previous version of the exam. So the questions, if the questions are asked by a professor once again, he will be able to score that. He does not have the general knowledge which allows him to answer the questions not seen previously. So overfitting in practice looks like you have a good scores on the training set, but they are not so good at the test set. So which of those phenomena we observed in those two examples? In the first place, it seems that our model was like the logistic regression was just enough for this representation, and possibly the problem itself. So this is a bit more complex thing. So maybe we didn't have enough data to make proper use of more complex models. And so this might take place with our random forest classifier. And you always need to remember that your training set needs to mimic the distribution of the production data. If not, the accuracy might not be very helpful. And most likely, the small data set which I have gathered initially was too small and was not accurate and enough to use the accuracy to tell more about the quality of the model. So that's why we show high accuracy scores with the random forest classifier. So let's go data to fix that. Let's try to add more data. Maybe we need to add memory to the whole thing, just to give the model a chance to see what was done previously, if the given asteroid was moved from left to right, and make a decision on top of that. We as humans are using this kind of hints to make a decision. So this, in fact, made the representation even more complex. That's why I was using the more complex models and add some more data. Nevertheless, it was still not enough to have some decent results. XGB classifier is the ensemble of decision trees which were grouped using the boosting paradigm. So the second one. So and those two complex models performed poorly, even comparing with our good old logistic regression. So dog barks into space and no one listens. So no results, no progress yet. So, but just to conclude those experiments, so increasing complexity of state representation when you don't have nothing which already works may not be the best idea, and it looks like the premature optimization. And as you know, premature optimization is a root of all evil, and is also a root of quite a lot of ML evil. So be aware of that. At some point, this project became a family hobby, family activity. My kids were interested in how I am. Games are much more attractive than our usual work, so it was quite fun to explain them what is going on here, what is going underneath. And they were quite interested, but I will spare you all my ups and downs and get to the representation, to the solution which worked a bit better. So let's split our game window as agreed, 6 to 8, And each cell in this grid will contain information about how many asteroids is there. Also, let's translate the position of the ship to this coordinate system. As you see, thanks to that, the amount of data, the complexity of representation is reduced quite a lot. A simple two-dimensional array, and let's see how it performs. So I've also added a memory to this, so the previous frame, but the solution performed quite okay. And as you see here, the neural network classifier was even able to get that he needs to move away from those falling rocks. And the result is much better than baseline, from the random agent, and also from the random forest classifiers. So we have some progress, but, and to conclude that, the good representation, so minimizing the complexity of representation helped. The representation still contained relevant information to make a decision. And I choose the right model. I experimented with quite a few of them. And a small amount of training data. So I didn't have to spend hours of playing to generate a proper amount of training data. It worked. Okay, so what's now? If you think about this game and what is the optimal strategy, you will surely get to the point when you will come up with the optimal way to solve this puzzle. So the optimal strategy here is to go from left to right, sorry, and fire a lot, just to keep the asteroids far from your ship. And this is, in fact, the optimal, the best strategy here. So what we were sneaking into those AI models is the knowledge that about this optimal strategy. And just out of, as a curiosity, I'll show you the simplest possible representation, which allows you to implement this optimal strategy. So the optimal strategy is, in fact, consists, in fact, of 127, 130 moves. And this, what you see here is a simple lookup table, and neural network is able to learn that also. Nevertheless, I am sure that all of you will agree that there is a simpler way, a lookup table, to implement such a strategy. So you need to remember one thing. If there is a known solution, if there is a known strategy, you most likely don't need machine learning. So you need to remember that introducing machine learning to your solution brings a lot of complexity. And you need to think twice and then think once again before doing that, because it will complicate your life. This makes a lot of sense if you have a large scale. So for example, we use machine learning a lot in Allegro to optimize search ranking, where even a small improvement gives us huge leverage and helps our users to find what they are looking for. Okay, but what about other games? We spent 30 minutes, 25 minutes on hacking one game, and we came up with a conclusion that we need to sneak in the strategy. What about general artificial intelligence? What about a solution which will be able to learn to play in any game we would like? So there are two, maybe more solutions here. I wanted to talk about two of them. One is evolutionary algorithm, and one is reinforcement learning. So in terms of evolutionary algorithms, question, are you really into gaming? So does it make you happy to see how the computer plays for you? You can even open several windows and look at this. What can be better than that? Most likely, and quite quickly, you will answer that two computers are better than one. And that's the correct answer. But what is better than two computers? A cluster of servers doing the evolution for us. Because what is crucial and what is interesting in evolutionary algorithms, that they can parallel quite nice. And we can look at Grafana or Kibana and see the progress. What is the progress of evolution, instead of looking at the screen and looking at how computer plays. And Pygame comes in handy here. It allows you to switch the game headlessly. So, but let's talk about evolutionary algorithms itself. In evolutionary algorithms, we work with population, which consists of individuals. And the individuals consists from are built from genes, which determine their behavior. Here, in the case of Shmoop, I was working with the population consisting of 6 individuals, and each individual was a sequence of moves. Because game contains some randomness, in order to evaluate the given sequence, I was running it 4 times and take the average score. And this evaluation ended, and we had I was choosing 4 individuals for the second round, and those 4 individuals were the subject of a crossover. So they were having kids, and crossover is the operation which swaps the half of the genome between the individuals. I also decided to leave the best sequence here for the second round, and the last stage before going into the next evaluation is to apply some mutations on the objects. So we're doing evaluation once again, and we were doing it as long as I saw the improvement in the population. If there was no improvement, I restarted the whole evolution once again. And one of the it was moving from left to right with a bit hesitation, which might cost life of the spaceship. Nevertheless, it came to the strategy which looks more or less like the optimal one. So this brings us to the carpet. No. This is not, in fact, a carpet. This is an experiment conducted by the scientists from Berkeley. And it shows you why this evolution needs to last, why exploration of such a solution space might take time. This is, in fact, a game board, and you see a bluish square is the player. And we, as a human who plays that game, we don't it will happen if we touch a black square. What will happen if we go on top of the black square or so? We need to learn that by playing the game. And it's hard. It's hard even for us to find the optimal strategy here. And this is the reason why the evolutionary or strategy or the reinforcement learning is so hard. Nevertheless, if you would play that game, you will most likely be performing like the reinforcement learning agent. Some of you may have heard about deep reinforcement learning and the experiments which DeepMind did with the Atari games, things like River Raid or Montezuma Return. And they were able to beat the human players by training. So no sessions, no training data. The agent was learning on his own. And the idea behind reinforcement learning is quite simple. It's something which we all have came through in school. So we have an environment, we are conducting different actions. We have a teacher who say if our action brought positive results or not, gives us rewards. And on top of that, we learn what we should do to succeed in this environment. Simple, but it brings quite a few challenges, computational challenges, because exploring of the space is a hard task. Nevertheless, the representation itself can be, when we can come back to our Shmoop example, can be quite similar to the. So we have a representation and we have rewards, and those rewards in our case might be scoring the asteroid, staying alive, and a negative reward for getting hit. What is different now? We had a classification, so on top of state we were applying class, and now we have a Q function which is intended to estimate the best possible, the highest possible reward for a given state and action. And this is something which is a sort of a continuous learning. And this estimator is getting better with every action. How this looks in pseudocode? In first place, we initialize QTable. So we initialize our estimator. You can think about this as a lookup table, as you saw on the previous slide. Nevertheless, this lookup table will be doable only for simple. But we can exchange it with a neural network, which is quite good in estimating the value of the function. So the whole thing goes while the agent is alive. We are getting the game state. We are trying to predict the best state, the best action for the given state. And then we are getting the reward, and we are trying to learn how to estimate the best possible action. So we constantly learn. And even when the agent died, the QTable remains filled with things which was learned from the previous gameplay. And that's how the whole thing goes. The DeepMind guys did it a bit different in terms of representation. We need to, in my approach, I had to hack every to come up with this representation. They decided to use pixels, so the view which is seen by a user. And they took 4 frames to have a memory of the game state. And thanks to using image, they were able to use some really neat things which originates from computer vision. I'm sure that you saw all those neural networks which are able to distinguish cats from dogs. And convolutional neural networks like ResNet or ImageNet are pretty good at that. The fun thing and the most relevant thing here is the transfer learning. So thanks to convolutional networks, we can take leverage of the neural network which was trained for something different. How this works? ImageNet contains millions of images, and the network itself was trained for general task like recognizing objects on the scene. And we can remove the final layers of such a network, add a new one, and train for our specific problems, as the DeepMind guys did. And the whole thing is called transfer learning, and it allows us to use convolutions. And those convolutions, you can think about them as a simple feature extractors. So they are extracting some feature of the image. Which feature, how relevant it is, it comes from the general training, from this transfer of knowledge. So we have a good network which can deal with image, and we can use it for different problems. But coming to an end, trained in that way look like after 4 hours of training. Guys, the DeepMind were able to overcome human players in most of the games, not all, but most. And thanks to using pixels, they were able to teach their agents even on top of the YouTube videos. There are OpenAI gym environments if you want to play with such a with hacking such an old games and using this kind of representation on your own. And the only thing which is required from you is to write your own agent here and to add the intelligence to that particular agent. So it's really nice to go there and try on your own. Problem representation is crucial. It cannot be too complex, it cannot be too simple. You need to contain data which are relevant to make a decision in a process which you are trying to automate. And decision about the problem representation is crucial for getting a proper amount of annotated training data. As supervised learning is still the most predictable way to apply ML, this is the biggest cost here. So choosing the right model is the next step, and you need to experiment at this stage and then apply hyperparameters, which are the parameters of the model itself. When you have working solution, you can adjust that and get even better results. I was already talking about the accuracy of the training data set, how well it mimics real data in production. If you have such a good representation in your data set, you can take advantage of offline metrics. From my point of view, a lot of fun. I also learn a lot of patience while waiting for those evolutionary results. I encourage you all to try something like this. If you are interested how I did that, all the source code is stored in GitHub repo. Go there. And if you have any questions, feel free to ask them now, or also reach me using my email or Twitter handle. Okay, if we don't have any questions, so thank you for your attention and sorry for some technical issues if you suffered from them. Thank you. Enjoy the rest of the conference, and as I said, I am available at Twitter or using email. Thank you.